Hello everyone, and welcome back to Band 7101 Business Analytics. In this module, we're going to introduce the data mining technique of classification and specifically examine decision trees. The learning objectives for this module are as follows. After this module, you should be able to define classification analysis as a data mining technique, build a classification model using a decision tree in RapidMiner Studio, and interpret the results of decision tree classification analysis in RapidMiner Studio. We've talked about how data mining works in a previous module, so essentially we are trying to extract patterns from data. And so far we've discussed clustering, which is an unsupervised learning technique. In other words, we are going into our analysis without any preconceived notions of what we are looking for. And specifically in clustering, we were looking at finding specific segments of the records that we had in our data. So in this module, we're going to be looking at a type of prediction pattern detection, and that is classification. So if we take a look at the data mining taxonomy again, we can see that classification falls under the umbrella of prediction. It is somewhat similar to regression, but is distinct from regression and time series analysis. There are several algorithms that can be used to classify data, including decision trees, which we'll talk about in this module, neural networks, support vector machines, k-nearest neighbor, naive Bayes, and genetic algorithms. And these are all supervised learning methods. So when we are trying to develop a classifier, we're going to have a target in mind that allows us to classify the data. So specifically in this module, we're going to look at the Titanic disaster dataset, and our target will be whether or not the passenger in the record we're looking at survived or not. So here we have a clear goal to be able to classify each record based on patterns in the data into the groups of survived or did not survive. Hence, this is a supervised learning technique. Classification is the most frequently used method of data mining, and it is part of the machine learning family. Like I said, it employs supervised learning. It learns from past data and then classifies new data. So two new concepts here that we're going to talk about when we talk about classification. That is the idea of a training set of data and a testing set of data. So when we develop your classifier, you're going to generally split your data into 70% training and 30% testing. This will allow you to test without overtraining and also see the actual performance of your classifier. The output variable in classification is going to be categorical in nature. If you're wondering what the difference between classification and regression is, so regression is also technically a classification technique that is a statistical technique. In this case, you're going to predict a continuous quantity, whereas using classification, you're going to predict a discrete class label. So like I said in the Titanic example, that would be whether or not the person survived. So that field would either be yes or no. But the two are very closely related. In terms of classification versus clustering, again, classification is a supervised learning technique and clustering is an unsupervised learning technique. When we talked about regression, we talked about different ways to assess the quality of our model. Specifically, we looked at whether or not factors in the model were significant, and then we also took a look at the R-squared value. There are, of course, other ways to assess that, but in terms of classification, we are going to assess the model by looking at the predictive accuracy of the model. So we're going to generate what's referred to as a confusion matrix, which essentially has the percentage of times that you were correct in predicting each one of the categories, and the percent that you were incorrect in predicting each of the categories. Classification models can also be assessed by the speed at which they process, as well as their robustness and scalability, as well as their interpretability. Here is a list of classification techniques. We will not be covering all of these in our modules. However, we will be taking a look at decision trees and neural networks, and we've already taken a look at statistical analysis. So these include decision tree analysis, statistical analysis, including regression, neural networks, support vector machines, case-based reasoning, Bayesian classifiers, genetic algorithms, and rough sets. Here is an example of a confusion matrix, which is going to be the primary source for accuracy estimation in your classification model, regardless of whether that is a decision tree or a neural network, and so on. So here's the math on this side, but we're going to focus on this diagram here. So here we have in each of these boxes the cases that we had true positive. So in other words, let's take the Titanic data example. So this would be that we predicted that record had a passenger that survived and that was a correct assessment of the classifier. On this side, we have a false positive. So we thought that they survived, but in fact they did not survive. Down here we have the true negative, so they didn't survive and we correctly predicted that. And over here the count of the times we thought they did not survive, but they actually did survive. So taking a look at this matrix will give us the overall accuracy of our classification model and give us an assessment that we can then report when we are sharing the results of our classification. Depending on the type of classification model that you are using, you will use a different training and testing set percentage. So if you are using a decision tree, you'll most likely use what's called a simple split, or holdout or test sample estimation. You're going to split the data into two mutually exclusive sets. So as I said before, a training set and a testing set. You take 70% of the records in your data and you train your classifier on that data. So you withhold 1/3 of your data, or 30% in this case, for the actual testing of your model. So you may be wondering, why don't you just use 100% of the data in your training set? Why can't we just develop the classifier based on all of the data? Well, if we do this, we will have completely overtrained the model. In other words, if we have fed every single record into our classifier, then we can say with 100% accuracy that we are able to classify all of the records. We won't really have learned anything about the accuracy of the model. If we withhold 30% for the purposes of testing, we can then feed each of those records into our classifier and see whether or not we were correct in predicting its target value. So for example, if we had a record in our testing set from the Titanic set and we passed it in and our model said, okay, that person survived, but they actually didn't, we would have that piece of information as part of our prediction accuracy and be able to report the accuracy of the model. When you are using a neural network, you're typically going to split the data into 3 subsets. So one for training, one for validation, and one for testing. And we'll talk about that in a later module. So you also may be wondering, if you're separating data into a training set and a testing set, how can we ensure that the training set has enough valid information in it in order to generate a good classifier? So one way of combating this issue is called k-fold cross-validation. So to minimize the bias associated with the random sampling of the training and holdout data samples in comparing the predictive accuracy of 2 or more methods, you can use a method called k-fold cross-validation. In this method, also called rotation estimation, the complete dataset is randomly split into k mutually exclusive subsets of approximately equal size. You then train and test the model the same number of times, so k times, and each time it is trained on all but one fold and then tested on the remaining single fold. So this technique minimizes bias associated with this kind of random sampling. Some additional estimation methodologies for classification include leave one out. So in leave one out, every data point is used for testing once on as many models developed as there are a number of data points. In bootstrapping, a fixed number of instances from the original data are sampled with replacement for training, and the rest of the data set is used for testing. This process is repeated as many times as desired. There's also a technique called jackknifing, which is similar to leave one out, but in jackknifing, the accuracy is calculated by leaving one sample out at each iteration of the estimation process. Finally, we can use area under the ROC curve, otherwise known as AUC, which is a graphical assessment technique in which the true positive rate is plotted on the y-axis and the false positive rate is plotted on the x-axis. The area under the ROC curve determines the accuracy measure of the classifier. So if you have a value of 1, you have a perfect classifier, which would probably indicate overtraining, whereas 0.5 indicates no better than random chance. So in reality, the values would range between the two extreme cases. The decision tree approach employs a divide and conquer method. So essentially, you are recursively dividing the training set until each division consists of examples from one class. In this process, you create a root node and assign all of the training data to it. You then select the best splitting attribute. You're going to find that the sex of the passenger on the Titanic dataset is going to be the best splitting attribute to start with, and you'll see why once we get into that example. You'll then add a branch to the root node for each value of the split. So essentially each field that you have, so in this case you have sex, you have fare, you have which class the person was in. Each of these will be added in turn as the data is split into mutually exclusive subsets along the lines of the specific split. So this process will be repeated for each and every leaf node until the stopping criteria is reached. There are several different decision tree algorithms, and they mainly differ on splitting criteria. So in other words, which variable, what value you're going to split on, the stopping criteria, so when you're going to stop actually building the tree, and whether or not the method employs pruning. So whether or not you're going to prune different branches based on whether they are useful or not. So the most popular decision tree algorithms include ID3, C4.5, C5, CART, CHAID, and M5. When you take a look at the RapidMiner Studio example, you're going to be introduced to the Titanic disaster dataset. So if you have not heard of the Titanic disaster, the Titanic was a British passenger liner that sank in the North Atlantic Ocean on April 15, 1912, after striking an iceberg on her maiden voyage from Southampton to New York City. Of the estimated 2,224 passengers and crew aboard, more than 1,500 died. This is a very popular dataset for the purpose of classification because we have a very clear target variable, and we have other fields that can be used to help us classify passengers into whether they survived or did not survive the disaster. You will use the classification method of the decision tree and the target, or as it will be called in the RapidMiner Studio, the label of survived. So if we take a look at this sample of data, we have 6 records here of passengers. You have the survived field, which indicates whether or not they survived or not, so a value of yes or no. The age of the passenger, the class of the passenger, so first, second, or third. The sex of the passenger, whether or not they were female or male. The number of siblings or spouses they had on board, which is an integer. The number of parents or children they had on board, and finally the passenger fare. So you can see that this data set lends itself nicely to a classification technique, and you'll be taken through this example in RapidMiner Studio. If you have any questions about this introduction to classification, please let me know.